Hello students, welcome to today's lecture of Theory of Machines. This is the part 3 of the lecture on differential band brake. In the part 1, we discussed about the constructional details of the differential band brake and learned about the direction of force applied in case when A is greater than B and when B is greater than A. We also discussed about the factors on which the effectiveness of the applied force depends, namely the direction of rotation of the drum, ratio of lengths A and B, and the direction of the force applied. We further discussed the first configuration of the differential band brake in which the distance A is greater than B and the force P is applied in the downward direction on the lever. We derived the equation of the force applied in both the cases in counterclockwise direction and in clockwise direction, and learned about the condition of self-locking in the case of clockwise rotation of the configuration. That is, if A is greater than B and force P is applied in the downward direction on the lever, and when the drum is rotating in the clockwise direction, if T2 by T1 is less than B by A, then the brake will be self-locking brake. In the second part of the lecture, we discussed about the configuration of the differential band brake in which the distance A is less than B and the force is applied in the upward direction on the lever. We then derived the equation of the force applied both in case of clockwise rotation and counterclockwise rotation, and learned about the condition of self-locking in case of counterclockwise rotation of the drum. That is, when A is less than B and the force applied is in the upward direction and the drum is rotating in the counterclockwise rotation, then if T2 by T1 is less than A by B, then the brake will be self-locking brake. We then compared the results of both the configurations and discussed that the first configuration, that is when A is greater than B, is more effective in the clockwise rotation, and the second configuration, that is when A is less than B, is more effective in counterclockwise rotation of the drum. We also discussed the case which is effective in both the directions, that is, we discussed about the two-way differential band brake in which the lever arms are made equal. So having discussed the analysis of differential band brake in detail, we can now move ahead to solve a numerical problem. So in today's lecture, we will solve a numerical problem, and in it we will see that how the two configurations of the differential band brake are more effective in one direction of rotation. And so in this way we will verify what we learned in part 1 and part 2 of the lecture. So let's see the problem statement. The problem statement is like this. A differential band brake has a drum with a diameter of 800 mm. The two ends of the drum are fixed to the pins of the opposite sides of the fulcrum of the lever at distances 40 mm and 200 mm from the fulcrum. The angle of contact is 270 degrees and the coefficient of friction is 0.2. Determine the brake torque when a force of 600 Newton is applied to the lever at a distance of 800 mm from the fulcrum. So as it is not given that which is the distance A and which is the distance B, so we can have both the combinations of the configuration of differential band brake. Like this is the case when A is greater than B, so this can also be a possible combination for this numerical, and this is the case when A is less than B, so this can also be a possible combination for this numerical. So we will do the analysis one by one in both the configurations, and the direction of rotation of the drum is also not given, so we'll consider both the directions in both the configurations of the differential band brake. So let's proceed with the solution. As always, let's write what is given. The diameter of drum is 800 mm, that is 0.8 meter. Therefore, the radius of the drum will be 0.4 meter. Angle of contact is 270 degrees. Force P is 600 Newton. The length L, that is the distance of the point of the applied force to the fulcrum, is 0.8 meter. Friction coefficient is 0.2. The distances A or B can be 40 mm. Similarly, B or A can be 200 mm depending on the configuration. And we have to find the braking torque TB when A is greater than B and P is acting in the downward direction. So this is the configuration, and we will consider both the direction of rotation of the drum, that is if drum is rotating in the counterclockwise direction or in the clockwise direction. So in this case, assuming that A is 200 mm and B is 40 mm, so the P must act in the downward direction as shown in the figure. Now the ratio of tensions is given by T1 by T2 is equal to e to the power of mu theta. Now keeping the value of mu and theta in this equation, we will get the ratio T1 by T2 as T1 by T2 is equal to 2.57. Now taking the counterclockwise rotation of the drum. So if the drum is rotating in the counterclockwise direction, then this side of the band will be tight side and this side of the band will be slack side. Tight side will be having tension T1 and slack side will be having tension T2. This can be identified by the red color. Now, as per our method, let's take moment about the fulcrum point O. For that, this is the free body diagram, which is having force P and tension T1 and T2. So the tension T1 rotates the lever in the anti-clockwise direction, so its moment will be positive, and the magnitude of the moment will be T1 into A. That is the perpendicular distance of the line of action of T1 from the fulcrum point. And the moment of force P will be in the clockwise direction, so it will be a negative moment, and the magnitude will be P into distance L, the distance of P from the fulcrum point. Similarly, the moment of tension T2 will be in the clockwise direction and the magnitude will be T2 into B. So the moment equation can be written as T1 into A minus P into L minus T2 into B is equal to 0. The moment of force P and T2 are negative moments or in the clockwise direction. Now putting the value of A, P, L and B in this equation, we have T1 into A. A is nothing but 0.2 meters from here, and T1 is nothing but T2 into 2.57. So T1 is kept as 2.57 into T2 from this equation, and P is equal to 600 and L is equal to 0.8 meter. This we have already, these are the given. P is equal to 600 Newton and L is equal to 0.8 meter. Now T2 into B. B is nothing but 40 millimeter, that is 0.04 meter. So from this equation we can easily find out the value of T2, and T2 is equal to 1012.7 Newton. Now putting the value of T2 in this equation, we can have T1 as T1 is equal to 1.012.7 into 2.57. This will give us T1 as 2602.5 Newton. Now the braking torque is given by TB is equal to T1 minus T2 into radius of the drum R. Putting the values of T1, T2 and R, we have TB is equal to 2602.5 minus 1012.7 multiplied by 0.4. The radius of the drum is given as 0.4 meter. So we have from this TB is equal to 636 Newton meter. Now considering the clockwise rotation of the drum. So it can be identified by the blue color in this diagram. So if the drum is rotating in the clockwise direction, so this side will be the tight side having tension T1 and this side will be the slack side having tension T2. So taking the moments about the fulcrum point in this free body diagram of the lever, we have T2 will rotate the lever in the anti-clockwise direction, so the moment will be positive and the magnitude will be T2 into A, and force P will be rotating in the lever in the clockwise direction, so the magnitude will be negative with the magnitude P into L, and similarly T1 will also be a negative moment with magnitude T1 into B. So we have the moment equation as T2 into A minus P into L minus T1 into B is equal to 0. So T2 is the positive moment and P and T1 will be having the negative moment. Putting the values of A, P, L and B in this equation and keeping T1 as T2 into 2.57, we have T2 into 0.2, A is 0.2 and P is 600 Newton, L, the length L is equal to 0.8 meter, T1 is 2.57 T2 from this equation, and B is nothing but 40 millimeter, that is 0.04 meter. From this equation we can easily calculate T2, and T2 is equal to 4938 Newton. So keeping the value of T2 in this equation, we get T1 as 12961 Newton. Now the braking torque can be calculated as TB is equal to T1 minus T2 into R. Keeping the values of T1, T2 and R, we get 12961 minus 4938 multiplied by 0.4. So TB is equal to 3101 Newton meter. So this clearly shows that for the same force applied, the braking torque is more in case of clockwise rotation. So as we discussed in the concepts of differential band brake, the clockwise rotation will be more effective when A is greater than B. Now let's see the second configuration, that is when A is less than B. So when A is less than B and P is applied in the upward direction on the lever, then this will be the configuration. You can see A is less than B. So assuming A to be 40 mm and B will be 200 mm and Px in the upward direction as shown in the figure. Now, as done earlier, the limiting ratio of tension is given by T1 by T2 is equal to e to the power of mu theta. So from here we will get T1 by T2 is equal to 2.57 as calculated earlier. Now considering the counterclockwise rotation of the drum. So in this case again the red color will identify the counterclockwise rotation. So if the drum is rotating in the counterclockwise rotation, then this side will be the tight side with tension T1 and this side will be the slack side with tension T2. Now taking the moments about the fulcrum point O, in the free body diagram of the lever as shown here, we have forces P, T1 and T2. So the moment of force T1 will be in the anti-clockwise direction, so it will be positive moment, and the magnitude will be T1 into the distance A, or the perpendicular distance of line of action of T1 from the fulcrum point, that is nothing but A. Similarly, the force P is also rotating the lever in the anti-clockwise direction, so it will also have a positive moment, and the magnitude of the moment of force P will be P into the distance L, that is the distance of line of action of force P from the fulcrum point is L, and T1 will be rotating the lever in the clockwise direction, so it will be a negative moment, and the magnitude of moment of T1 will be T1 into the distance B. So writing the moment equation, we have P into L plus T1 into A minus T2 into B is equal to 0. P and T1 are having positive moment and T2 is having negative moment. So keeping the values of various parameters, we have P is nothing but 600 Newton, L is 0.8, T1 we have kept from this equation as 2.57 into T2, and A in this configuration is 0.04 meter and B in this configuration is 0.2 meter. So from this equation we can calculate T2 easily. So T2 is equal to 4938 Newton. Now keeping the value of T2 in this equation, we have T1 as 4938 into 2.57. This will give us T1 is equal to 12619 Newton. Now braking torque again can be calculated by TB is equal to T1 minus T2 into R. So putting the values of T1, T2 and R, we have TB is equal to 3101 Newton meter. Now considering the clockwise rotation of the drum. Clockwise rotation is identified by the blue color in the diagram. So if the drum is rotating in the clockwise direction, this side of the bell will be the tight side having the tension T1 and this side of the bell will be slack side having the tension T2. So now taking the moments in this free body diagram of the lever about the fulcrum point O, we have T2 will have the positive moment in the anti-clockwise direction and P will also have the positive moment in the anti-clockwise direction and T1 will have the negative moment in the clockwise direction. So the magnitude of moment of T2 will be T2 into A and magnitude of moment of force P will be P into L and magnitude of moment of T1 will be T1 into P. So writing the moment equation, P into L plus T2 into A minus T1 into B is equal to 0. Now putting the values of various parameters, we have P is 600 Newton, L is 0.8, A is again 0.04 and T1 we will keep as 2.57 into T2 from here and B is 0.2 meters. Now solving for T2, we have T2 is equal to 1012.7 Newton. Keeping the value of T2 in this equation, we can get T1 as T1 is equal to 2602.5 newtons. Now braking torque can be again calculated by TB is equal to T1 minus T2 into R. So keeping the values of T1, T2 and R, we have TB is equal to 636 Newton meter. So we can observe that in this case TB is more in counterclockwise rotation. So for the same force applied, counterclockwise rotation of this configuration will be more effective as discussed earlier. So when A is less than B, the counterclockwise rotation of the drum will be more effective. And you can observe one more thing, that the value of braking torque in this configuration obtained in the counterclockwise direction was similar to the value of the torque obtained in the previous configuration, that is when A is greater than B, in the clockwise direction. So the value of torque is just interchanged by the direction of rotation of the drum. So we observe here that the results show that effectiveness of the brake in one direction of rotation is equal to the effectiveness of the other if the distances of the pins on the opposite sides of the fulcrum are changed. That is when A becomes B and B becomes A, and the force is applied in the proper direction so that the bend is tightened. This means that the effectiveness of brake in one direction, in this case the counterclockwise direction, is equal to the effectiveness in the other direction. That means in the clockwise direction when the values of A and B are changed. So this is how you solve the numerical problem for differential band brake. Do solve more problems from your textbook, and in case of any doubt, please feel free to contact me. Thank you.